Okay, so I did this one before, and then I realized that my audio was all messed up due to Wi-Fi issues. So I'm going to go through this document slowly, in which I sketch the function given here. So why don't you pause the video now and write all this down. 1, 2, and just 1 and 2 for now. Okay, so domain. Okay, so for domain, I'm asking, okay, what x values am I allowed to plug in here? Well, anything but 0, right? Okay, that's easy enough. Okay, y-intercept. Okay, to find the y-intercept, I would set x equal to 0, but here I see that I cannot. So there is no y-intercept. I never touch the y-axis. X-intercept, I set y equal to 0. So well, f of x equal to 0. Try to solve, but what happens is that this quadratic, I can't set it equal to 0 and get an answer. Okay, I know that because b squared minus 4ac is negative. Okay, 3 is what's happening for large x values. So in the preceding video, we called this horizontal asymptotes. We found these limits to find horizontal asymptotes. Okay, so if I look at this expression here, I see that the x and the 1 don't matter. You have x squared over x squared. So the limit is 1 in both cases as x goes to plus infinity or minus infinity. So these are going to be my horizontal asymptotes. So maybe you want to pause the video and write this down. So my horizontal asymptotes are y equals 1 in both directions. Okay, so I got like a 1 here, and then you'll have a asymptote like that. And I think we'll see later on. I think the function goes like this, goes like that. So that's the x goes to minus infinity, gives me that chunk. And x goes to plus infinity is going to give me something like that. Okay, so that's what I found in part 3, and also part 4 for the horizontal asymptote bit. Vertical asymptote. Okay, my function has division by x. So when x is 0, I get my shooting up to infinity. And I believe that's going to give me something like this, also like this. Anyways, we'll come to that later. Okay, let me scroll down to cover 5. So pause the video. Right. So I take a derivative. I'm not showing my work here. Fill in the blanks if you're at all concerned. Take a derivative, set it equal to 0. Okay, the numerator must be 0. So x has to be minus 2. That gives me the minus 2 on my number line here. The 0 on my number line, which is an important thing to remember, that is my vertical asymptote. Okay, so always put vertical asymptotes on your number lines for 5, and also later on in 7. We're going to have it on our concavity number line. Okay, what do? I just use test points to decide whether my function is increasing or decreasing. So I would probably do minus 3, minus 1, and plus 1 to get these, minus here, to get these arrows. Okay, so let's scroll. Okay, 6 and 7. Take a second, pause the video, write these down. 6 is the local min. So we want it happens at minus 2 here. Okay, but in 6 here, I'm asking you to find the corresponding y value. Okay, so to get your marks, to get your grades here, you need to actually plug -2 into your original function and calculate the y value. And it's a local min because of what I found up here. You see how it's decreasing and then increasing afterwards. So my min right there. 7 is concavity. Find a second derivative, set it equal to 0. Maybe pause right now. Copy this down. Second derivative, set it equal to 0. Numerator must be 0. So x is -3. That gives me this -3 on my number line here. And the 0 is my vertical asymptote. Test points to get the pluses and minuses. Plus gives concave up, minus gives concave down. Okay, 8. What is 8? 8 is, I got to calculate that inflection point. So at -3, we can see concave down before and then concave up afterwards. So that is indeed an inflection point because the function is continuous here. At 0, that's a vertical asymptote. Okay, so even if concavity changed, it would not be an inflection point. Okay, vertical asymptotes they're just vertical asymptotes. They can't be inflection points. They can't be local maxes or local mins. Let's scroll up here just to, here's a good. You'll notice here, look, my function is increasing and then it's decreasing, but 0 is a vertical asymptote. So it's not something I worried about in number 6. Okay, it's a vertical asymptote, not a local min, not a local max, even though I'm increasing before and decreasing after. So I calculate the corresponding y value for my x equals -3, and I state what the inflection point is. Okay, now I'm ready to graph this thing. The first thing I'm going to do is put these points I have. I got the inflection point there. Put that on there. I also got a local min here. X is -2, y is 3/4. This is going to be a bit awkward to draw. It's not good. So it was -2 and 3/4. That's roughly, well, I'll say there. And -3 and 7/9 is a little bit higher. It's there. Sorry, I have a dot here at 0, 0. Just ignore that. Okay, y equals 1. We decided earlier that's a horizontal asymptote. So that's why I have the y equals 1 line in dots there. Okay, so where am I? I have a min at -2 and an inflection point. Okay, just so if I look at my concavity diagram, I am concave down until -3, and then afterwards I'm concave up. But I got this horizontal asymptote. Okay, so what does that mean? It means my function is going like this, or it's going like this. Well, given these dots here, I'm going to take the bottom one, right? So I'll take the bottom one. And I'll start drawing. Remember, I am concave down. So concave down, 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 down. Now it's switching right at -3. It's hard to get this, especially on a tablet here. Ooh, am I touching the mic? So here I'm respecting my horizontal asymptote. I'm concave down until I get to -3, and then I'm going to be concave up, and then I'm going to have a min right here. So this is really cramped here. You should give yourself more space. So concave up, 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 up. Okay. And then there's a min there. It starts going back up afterwards. What's next? Vertical asymptote, the y-axis, x equals 0. So my function is either doing this or it's doing this. Well, you see how my function has already started to curve back up. So I'm just going to continue and connect the dots like that. Oh, that's really awful. Oh, that's even worse. Whatever, I'm just going to leave that. Put a little arrow on top. How do I know it doesn't do something like woo like that? Well, if it went woo like that, I would have a max here, right? A local max. But I never found that earlier, so not possible. Okay, next. X equals 0, vertical asymptote. That means I have something like this, or maybe something like this. Well, which one is it? Well, this is concave up here, and this would be concave down. If you look at my diagram, it's got to be, oops, concave up. So I'm going to delete the one on the bottom here. That's not the one I want. Now, I have this horizontal asymptote over here I have to respect. So my function's either doing this or it's doing this. It's approaching y equals 1. Well, okay, the most natural thing is just to go like this. Yeah. Okay, concave up, right? Again, how do I know it's not doing something like that? Well, again, there would be a min there. I would have found a min earlier, but I did not find it. So, all right, there you have it. I know that was quick. One little detail. Oh, put an arrow there, and label your inflection point because it's often difficult. Oops, I deleted my chunk here. Label your inflection point. It's often difficult to make that visible. What else? Oh, look, you see how I'm crossing? Look at this point right here. This is a bit weird for a lot of students. I'm crossing my horizontal asymptote. That is totally okay. If you think about it, a horizontal asymptote tells me what's happening way over here or way over here. Okay, it doesn't, what's happening in the middle, you know, that y equals 1 I found, it has no effect on what's happening near the y-axis. Okay, so it's okay. There's no problem crossing the horizontal asymptotes.